This is part 2 of section 4.4. We are looking still at curve sketching and sort of appreciating what calculus tells us about where functions have maximums and minimums, where they're concave up and concave down, and really helping us get a good picture of the graphs. Okay, so I am looking at number 10. And in this problem, we will be considering y equals x times the ln of x squared. So the other thing that's great about these problems is that we get to sort of review the world of derivatives, which I know you're already really good at. But okay, I'm going to write this as f of x because I like to do that. And of course, we're going to have a u and a v when we're doing our derivative here. This is the u and this is the v. But before we start, we should always think about the domain. So what is the domain of this function? What do we remember about the natural logarithm?
Has to be value squared equal 0.
Very nice. Okay, so the domain is from 0 to infinity. Okay, you can't take the log of a natural number, a negative number, because remember, the logarithm undoes exponentiation. So the log of the ln of 2 means e to what number is 2? Well, so the base e. E to no number will be negative, and e to no power will be 0. So the domain of the logarithm is from 0 to infinity. Okay. And we just want to remember that because as we're working through these problems. All right, let's, the first thing, so that was step 1 was domain, and then we have to think about symmetry. F of negative x is equal to negative x times the ln of negative x squared. Well, we can't even, because if we take the opposite of x, then it's it's just no. So this is not equal to f of x, or the opposite of f of x. So we have no symmetry, which we wouldn't really be expecting anyway, since we have a restricted domain from 0 to infinity. How is it going to have symmetry across the y-axis? Okay, or the origin. I guess, no, even the origin it can't do. All right, so let's take the derivative. That's step 2, I think. So f prime of x, if you have, let's see, should we do this in red? If we have u equals x, u prime is equal to 1. V equals the ln of x quantity squared. So v prime equals, using the chain rule, 2 ln x times the derivative of ln x, which is 1 over x. Everybody remember that? Okay, and so then, how's it go? U times v prime plus v times u prime? Okay, and so we have u, which is x, times v prime, which is 2 ln x over x, plus v, which is the ln of x squared, times u prime, which is 1. So our derivative, the x's cancel here, we get 2 ln x plus the ln of x quantity squared. That's my first derivative. And then my second derivative is actually easier to compute. Does Robinson want to tell me the second derivative? Are you talking? Robinson, you're turning around. Tell me the second derivative. I gotcha.
Dun, dun, dun.
Please tell me the second derivative. Are y'all talking? Unmute, Robinson, and tell me the second derivative.
You're
messing up my video.
We are unmuted. We're just working on it.
You're pondering it?
Yes.
Well, you're slow. MCC, do you have it? 2 over x plus 2 ln x times 1 over x. There we go. So, see, that wasn't that hard, Robinson, was it?
No. Sorry.
Yeah. All right, so watch out. I'm going to get you again. So this is 2 over x plus 2 ln x over x. Can I cancel these x's right here because I don't like them? No, it's not allowed. Okay, because the ln owns that x. All right, critical points. How do I find the critical points, Robinson?
Look,
Make it equal to 0.
Yes, that's much better. Set your derivative equal to 0. So 2 ln x plus the ln of x quantity squared equals 0. This looks kind of scary, but it's really not so bad. What you're going to do is factor this. So this will be ln x parenthesis 2 plus the ln of x equals 0, right? And then you set each of your factors equal to 0, ln x equals 0, or 2 plus the ln of x equals 0. So when is it true that, or how do we solve these? Do you guys remember how to solve like ln x equals 0 from pre-cal or college algebra?
Say yes.
Yeah, you kind of, like, I call it you E it. Like, so if you do E here and E here, like you E it, e to the ln x is just x, because they undo each other, and e to the 0 is 1. The other way you can do it, I used to call it like the circle of life. The ln of x equals 0. So this, I know this is base e. E to the 0 equals x. So this is the power, and this is the answer. E to the 0 equals x. Does that make sense? Either way, you should get x equals 1. The ln of 1 is 0. All right. On this one, you'll have ln x equals negative 2. So you can e it. If you e it, you get x, because e to the ln x, those undo each other, you just get x, equals e to the negative 2, or 1 over e squared. So those are your two extremely uncomfortable critical points, right? So what we do with those critical points is this is where we can determine where the function is increasing or decreasing. So we will draw a number line, and we will place e to the negative 2 is going to be a number less than 1, because it's 1 over 2 points, whatever. So e to the negative 2, and then 1 is here. Now, we remember our domain on this function is from 0 to infinity, so I shouldn't have an arrow here. I should have a 0. Okay, so then we have to pick a number between 0 and e to the negative 2, and so like e to the negative 3 would be a good one to pick. So if you test e to the negative 3 into your derivative, let's see, so we could test e to the negative 3. You would do f prime of e to the negative 3. And remember, all you're trying to figure out is whether it's positive or negative. So let's see if we can do this without a calculator. It could be challenging, but I think we can do it. So this is going to be 2 ln e to the negative 3 plus the ln of e to the negative 3 squared. Okay, well, what's the ln of e to the negative 3?
Negative 3.
Good. So this is 2 times negative 3. See, the whole thing is that the ln and the e undo each other. So you just get the number, or the power rule, the negative 3 comes in front, and the ln of e is 1, however you want to remember that. Plus, and then this is ln of e.
9.
Yes, thank you, Robinson. This is negative 3 and then squared, which is 9. And so all we really care about is that this is positive. So this is actually 3, which is greater than 0. So between 0 and e to the negative 2, it is positive. Now, if you're having a bad day, you could just, figure out what e to the negative 2 is on your calculator and pick a number less than that and plug it in with your calculator and figure out that it's positive. But you kind of take away your learning fun when you do that. All right, now a number between e to the negative 2 and 1 would be what? E to the negative 1 might be a fun number to test, right? Do y'all agree that e to the negative 1 is?
0.
0? Well, no, 0's over here. Oh, e to the 0 is 1. So e to the negative 1 will be larger than e to the negative 2. Do y'all agree with that?
You big idiot.
Half. What? Are y'all being nice? You better unmute. Did she call me an idiot? Man, I hope you were talking about someone
That
else.
was insulting me. I'm sorry.
Whatever, I'm fine. Idiot. God, that's mean. 2 ln e to the negative 1 plus the ln. Who is that? Isn't that one of the students that's like, who said idiot? Little orange shirt girl. Was it her? You better, she's moving the mic now. She's not even going to talk to me. Oh, wait.
Yeah.
Is she not talking? Yeah. Get it away from me. What is on her? What's on your shirt? Oh, we'll have to, you're ruining my video. What's on your shirt? Trinity? Does that say Trinity?
Yes. Yes, in San Antonio.
Oh, yeah.
I think she's aware of where Trinity is.
Why? They're doing
Is that where you're going to go?
No, this is where my older brothers go. I want to go to Stanford, actually.
Oh, I didn't hear any of that. What?
This is where my older brothers go to Trinity, but I want to go to Stanford.
Are you going? Are you in?
Not yet.
You haven't heard yet?
She went this summer though.
Wow, I went to St. Mary's University in San Antonio, so which is
Oh, yeah?
they're kind of Trinity's close or whatever. It's a good school.
I know people that go there. It's a nice school.
It was nice. We had, except they had. I don't know if they're still like this. We had this ad. Like Father Motor was the president of the university at the time, and they had this ad. They have like this pond and this green grass, and they had Father Motor out there and all these little, like a gaggle of students around him, and the song was St. Mary's, a loving learning kind of place. Like it was a pre-K or something. It was just, I was like, loving learning. It was weird. But I think it's better now. I think it's more hip. All right, back to calculus. I was going to give you a hard time about something, but I forgot because I got distracted by your shirt. All right, here, let's finish this problem. I was back in college. All right, so if e to the negative 1 here is, this is going to be, we're going to have, what are we going to have here? This will be 2 times negative 1, and then this will be the ln of e, this is negative 1 squared, which is 1, so this is less than 0. So we're negative. And then if we pick a number greater than 1, like 10,000, f prime of 10,000 is going to be equal to 2 ln 10,000 plus the ln of 10,000 squared. All you care is that that is greater than 0. So it's positive. Okay. So we must increase and then decrease, decrease and then increase. So we must have a max here and a min here. We could have used the second derivative test to determine if we have maxes or mins as well. Okay. And so this is the interval where we increase, then we decrease, and then we increase. So we will come over here, and on step 4 then, we will say that we are increasing from 0 to e to the negative 2, union 1 to infinity, and we are decreasing from e to the negative 2 to 1. All right, now, number 5 is our points of inflection. Okay, how do we find points of inflection? Good, find where the second derivative equals 0. So our second derivative was, what was it? Our second derivative was 2 over x plus 2 ln x over x. So I'm going to put that all over x. So this is 2 plus 2 ln x all over x. See where that equals 0. Or is undefined. It's actually undefined at 0, but 0 is not in the domain, so you're good to go there. So all we have to do is figure out where the numerator equals 0. So 2 plus 2 ln x equals 0. A fraction equals 0 when the numerator equals 0. So this is going to be the ln of x equals, I move the 2 over, divide by 2, so that's negative 1. Then I e it, and I get e to the negative 1, right? So e to the negative 1 is my critical point. So if I put e to the negative 1 on a number line, this is 0. Here's e to the negative 1. If I test e to the negative 2 into the second derivative of e to the negative 2 will be 2 plus 2 ln e to the negative 2 over negative 2. All I need to know is whether this is positive or negative. Can anyone tell me?
Not over here.
You're so smart. Good. Over e to the negative 2. Thank you very much. Can y'all tell me whether this is positive or negative?
Positive.
It's going to be...
Okay.
Zach said negative. He said positive and then he said
It's going to be, this negative 2 comes in front, right? And like the power rule. And so this is going to be 2 plus negative 4 over e to the negative 2. So this is a negative in the numerator. E to the negative 2 is 1 over e squared, which is still positive. So this is a negative over a positive. So I'm going to say less than 0. Negative? Okay. And e to the negative 2 is in here, right? E to the negative 2 is to the left of e to the negative 1. Right? Okay. And so if I pick a number greater than e to the negative 1, like 1, I will get, or e to the 0, which is 1, I will get a positive value. If I test test 1, that's going to be f double prime of 1, which is going to be 2 plus 2 times the ln of 1 over 1, which is greater than 0. The ln of 1 is 0, so this is just 2 over 1, which is positive. Okay, so I have a point of inflection here. I'm concave down and then concave up. So I'm concave down from 0 to e to the negative 1, and I'm concave up from e to the negative 1 to infinity. And so I will say that I have a point of inflection at the point e to the negative 1, comma, f of e to the negative 1. So I have to put e to the negative 1 in the original function. The original function was x ln x squared. Remember, f of x was x ln of x squared. So f of e to the negative 1 is e to the negative 1 times the ln of e to the negative 1 squared. What's the ln of e to the negative 1 squared? Say it again? 1. And so this is just e to the negative 1. All right, so that's my y coordinate. So this is the coordinate e to the negative 1, comma, e to the negative 1. Are you just completely uncomfortable with all this e stuff? It's fun. All right, do we have any asymptotes? No asymptotes. No asymptotes. Because, you don't have a denominator. And we just know that ln, we can't, because our domain's from 0 to infinity. All right, and so we decided that we have a max at, our max was at e to the negative 2, and our min was at 1. So we have a max at e to the negative 2, comma. If I plug e to the negative 2 in here, it will be 4e to the negative 2. We had a min at 1, comma, this is 0, because the ln of 1 is 0. So this will be 1, 0. And that's my x-intercept. And I don't have a y-intercept because I can't plug 0 into the domain. Okay, and then if I were to sketch a graph of this, and you probably at some point are going to have to get a sense of what e to the negative 1 is, what e to the negative 2 is, and all that sort of stuff. So at some point you have to sell out and get your calculator. E to the negative 1 is 0.36, and then e to the negative 2 will be smaller than that at 0.14. So 0.37 and 0.14. 0.14, and then this is 0.37. And let me see what 4e to the negative 2 is. 4 times e to the negative 2 is about 0.54. 0.54. Okay, so we have a min at 1, 0, a max. Okay, so it looks like we could call this can be 1, and this can be 1. And then 0.14, 0.54, so just kind of about right here, we have a max. We know it starts at 0, and then we have a min at 1, 0. And we have a point of inflection at e to the negative 1, which was 0.37, 0.37. All right, so it's increasing, and then it decreases, and then it changes concavity. I don't know, maybe yours looks better than mine. And then it has a minimum, and then it goes up like that. All right, and what's interesting about this problem is if you first graph it, if you just graphed it in the standard window, you would have no idea of that little bit of action that's happening between 0 and 1. Do you see how small it is? You know what I'm saying? Like if you just graph the original problem, which was x ln x squared, and you just did it in the standard viewing window, it's probably not going to be apparent to you that something interesting happened. Although you can sort of see this. You know, you do sort of see that. So you may feel like you should change your window to look at it between maybe -1 and 1 and see what's happening. But that may not be, you know, your first thought. Isn't that awesome? It's great. Okay. Another problem. Okay, now for the problems 11 and 12, the first derivative of a continuous function is given. Find the second derivative and use steps 2 through 5 of the graphing procedure to sketch a general shape of the graph. Okay, so this is kind of the exciting stuff here, is that once if you know the derivative, you actually can determine a lot about the original function. Because if you know the derivative, you can find the second derivative. So you can see maxes and mins and concavity and increasing and decreasing. So you know the entire shape of the original function. You just don't know where the original function is located. You know what I mean? Or kind of where the max and mins are located, but you know, I mean, you don't know what they are. You know where they live, though. You don't know what the y coordinates are. Okay, so this second derivative of this problem is 1 minus 2x. Do y'all agree? All right, well, the first derivative equals 0 at 2 plus x minus x squared equals 0. I like to factor out a negative because I'm a positive person. So this is x squared minus x minus 2 equals 0. And then I can factor that as x minus 2 times x plus 1. So x equals 2 or negative 1. All right? So those are my critical points. And I can actually, just for fun, let's use that second derivative test to determine whether these critical points are maxes or mins. All right, so the second derivative of 2 is 1 minus 2 times 2, which is negative 3, less than 0. So what do we have at 2? If we are negative, meaning concave down at 2, then 2 must be a, good, 2 is a max. F double prime of negative 1 is 1 minus 2 times negative 1, which is 3, which is positive, which means you're concave up at negative 1. If you're concave up at negative 1 and it's a critical point, it must be a min. So that was using that fun second derivative test. Okay, you could also have used the number line. If you looked at the number line and you plugged in, let's see, negative 1 and 2 into your first derivative, you can also kind of know, since this is a max, you can probably argue that if it's a max, it's going to have to be increasing and then decreasing, and then this is decreasing and since it's a min. But you could also test numbers. For example, if you test 0 into the first derivative, you do get a positive, right? So we know that the function is decreasing, then increasing, and then decreasing. If we wanted to look at concavity, we need to see where this equals 0. And so that would be this is the, what is that? That is the second derivative. That is 1/2. So we have a possible point of inflection at 1/2. If we investigate the second derivative to the left of 1/2 by choosing a number like 0, we see that it's positive. If we put a positive number into the second derivative, we get 1. Like if we put 0 into the second derivative, pick a number greater than 1/2, like 7,000, you'll see 1 minus 14,000 is in fact negative. So this means the function is concave up and then concave down. Okay? So if you wanted to sketch a general shape of the original function, you don't know where the points are located. If you could just have one point, you could do a better job, but you don't. You don't have anything. But you do know, well, you know where, you don't know where on the y-axis. You do know that you have a min at -1. So it does. I don't even know whether it's up here or down here, but I'm just going to guess that it's there. I don't know that, though. I do know that at 1/2, I change concavity, and then I know at 2, I have, that doesn't look very good. So this is 1, 2. So at 1/2, let's say maybe about here, I change concavity, and then at 2, I know I have a max. So I don't really know anything other than a general shape like this, and then I got to sort of change my concavity, and then like that. Now this could be located anywhere along the y-axis, and this could be steeper. These maxes, there could be a greater difference in the max and min. But I have, at least I know where it bends. Okay? So that was fun. And I know the intervals that it's increasing or decreasing. Okay, so that one was fun. Number 12 is also a thrilling problem. Let's find the second derivative. We'll have a quotient rule here. This will be my u, this will be my v. U is equal to x to the -2/3. So u prime is going to be -2/3 x to the -2/3 minus 1, which is -5/3. V is equal to x minus 1, so v prime is equal to 1. So it's u times v prime, so that's going to be x to the -2/3 times 1, plus v times u prime, which is x minus 1 times -2/3 x to the 5/3. All right, this is going to be interesting. All right, so this is 1 over x to the 2/3 plus -2 times x minus 1 over 3x to the 5/3. I want to get a common denominator. So Robinson, what will my common denominator be?
We are pondering.
Yeah.
Wouldn't
3x something.
Yes, 3x to the
10/3.
That's actually a decent guess, but no. Actually, we can use 3x to the 5/3 as our common denominator. All that this x to the 2/3 will need is a 3 and an x to the how many thirds? What will this need?
3/3.
Yeah, 3/3 to make 5/3.
2/3 and 1.
So actually, it just needs 3 over x.
3x.
Y'all even? Okay.
Yeah.
All right,
we
see you
gotta
later.
go.
So 3 over x over 3 over x. Does that make sense to get the common denominator there? Okay, so this is going to be 3x minus 2x plus 2, just distributing over there, over 3x to the 5/3. Remember, calculus is all about learning how to do algebra. So that's what we're doing here. We're reviewing our algebra skills. Okay, why do we need to get a common denominator? Why do we care about this common denominator? Okay, or to find points of inflection, right? We've got to figure out where this function equals 0, right? You're always looking for where the derivative equals 0. So in this case, this will be x plus 2 over 3x to the 5/3 is our second derivative. So we have possible points of inflection Where? At, excellent, x equals negative 2 because that makes the numerator 0, and 0 because that's where the second derivative is undefined. So you have to check that as well. Okay, and so what about that first derivative? We didn't look at him too much. We just jumped right into the second derivative. But here's the first derivative. It is x minus 1 over x to the 2/3, like that, because it was x to the negative 2/3. So these are critical points. Where are the critical points for this one? X equals 1, and then also 0, because it's undefined. So we either have a vertical tangent or a cusp at 0. And it's most likely going to be, well, I'm not going to say that. Never mind. Okay. So let's do some investigations. Let's look at the first derivative at its critical points at 0 and 1. We know that this is either a vertical tangent or a cusp. We know that 1 is a max or a min. If we pick a number between 0 and 1, will we get a positive or a negative in our first derivative? Yeah, you could test like 0.5, right? And so y prime at 0.5 is going to be, do y'all see how it'll be less than 0? It'll be negative because it'll be 0.5 minus 1. And 0.5 to the 2/3 is positive, but 0.5 minus 1 is negative, so you have a negative over a positive. If you pick a value greater than 1, like, so this is in y prime. If you pick a value greater than 1, like 2, you're definitely going to have a positive. And if you pick a value to the left of 1, like negative 5, what are you going to have? Let's see. The denominator will always be positive. Why? Because you're squaring it. Even though the cube root of negative 5 is negative, when you square it, it's positive. So you just have to worry about the numerator. And the numerator at negative 5 is negative. So we are negative, right? Okay. So what do we have here? Well, it's not a flattening. And the reason we know it's not a flattening is because it's undefined. The derivative is undefined at 0. So it has to be a vertical tangent. It would be a cusp if you changed from increasing to decreasing or decreasing to increasing. Okay, so we have a vertical tangent here and we have a min here. So a vertical tangent, a decreasing vertical tangent means you kind of just come in and then you get really, really straight like that. And then a min looks like that. Okay, and so we know that we are decreasing from negative infinity to 1, and we are increasing from 1 to infinity. And let's look at our second derivative. So our second derivative, we had possible points of inflection at negative 2 and at 0. Now in our second derivative, if we test a number like y prime of negative 3, when you plug that into your second derivative, here's my second derivative. Where is it? X plus 2 over 3x to the 5/3. You're going to get a negative over a negative, so that's going to be positive, right? If you pick a number like, negative 1 into your second derivative, negative 1 into my second derivative, I'm going to get a positive divided by a negative. So it will be negative. And if I put a number like 10, I will get a positive over positive, so it's going to be positive. Y greater than 0, so like 10, it's positive. So I'm concave up, concave down, concave up. So at that vertical tangent of 0, I actually change concavity. Okay? So when I'm sketching this graph of the original function, I have to do some interesting things. So I have points of inflection at both spots, 0 and -2, because I changed concavity. At -2, I know that my function is decreasing all the way to 1. It's always decreasing, but it changes from concave up to concave down somewhere at -2. And then at 1, I actually have a minimum, and I'm concave down. And at 0, I have a vertical tangent. So somewhere like maybe here at 0, I have a vertical tangent. So maybe I'm going to make this a little bit taller. And what do I have at 1? I have a min. Okay, so I'll try it like this. All right, so I'm decreasing and concave up until 2, until -2. Decreasing and concave up. Then I actually change concavity, but I'm still decreasing. And I become very, very vertical, and then I change concavity again at 0, and then I'm concave up from 0 to infinity. So all of this is concave up. So this didn't turn out very well, but this vertical tangent here is also a point of inflection. All right, so that's kind of fun. Okay, and we will work the following problems from the textbook. Pay close attention to them because they are not covered on the online problems, but you will see them again. I like these problems. All right, so here's the first and second derivative of the function, and you have to copy the picture and add it to a sketch of the approximate graph of f, given the graph passes through the point P. So basically what I want you to do is I'm giving you first and second derivative. You have to graph the original function. All right, so if this is the first derivative right here, right, I could call this like A and B, and maybe I'll call this C. Why do I care about where the first derivative crosses the x-axis?
Because it tells you where those are your proof.
Right. A and B are critical points for the first derivative because that's where it crosses the x-axis. To the left of A, what is the derivative? Your choices are positive or negative. It's above the x-axis, right? So it's positive. Between A and B, the derivative is below the x-axis, so it's negative. And then from B to infinity, you're above the x-axis, so you're positive. What does this tell you about the original function? It tells you that you have an increasing and decreasing change at A, so you have a max at A, and then you go from decreasing to increasing at B, so you have a min at B. The original function does. Okay? And you also know the interval where the original function is increasing and decreasing, because that's where the first derivative is positive. All right. Now the second derivative has a critical point at C. This is my second derivative, is negative to the left of C, which means it's what is the original graph is doing what in terms of concavity?
Concave down.
Good, concave down. And then it's positive, which means the graph is concave up. Everybody happy? So at C, we have a point of inflection. So at this point, we're going to need to change concavity. All right? So A is a max. Now, we don't know where the max occurs. Say I just put it here. This is going to be, now I'm graphing the original function in green. I'm just going to put the max there. I know that this is a point of inflection. I'm going to put the min, I don't know where. I know it's at B, but I'll just maybe put it like this. Okay, so I'm increasing, I have a max, and I'm concave down. And I stay concave down until C, where I switch, and now I'm concave up, and then I have to have a min at B. So the green is f of x.
So C is just where the y-intercept is? Why is that?
No, C is where this pink line crosses the x-axis. It doesn't have to do with it just happens that the pink line crosses at 0. The second derivative is 0 at 0.
Oh.
Okay? All right, so here, this will be my A and this will be my B. These will be important points. Let me do this in black. For the first derivative. And then the second derivative crosses right here, right? So A, B, C. A and B. What is the first derivative doing in terms of being positive or negative to the left of A? Well, it's actually increasing if you are going to, the original function is decreasing because the first derivative is negative. Between A and B, the first derivative has positive y values, which means the original function will be increasing between A and B. From B to infinity, the derivative has negative y values, which means the original function will be decreasing. Using where the second derivative is 0, where the second derivative crosses the x-axis, it is to the left of C positive, which means the original function is concave up there. Then it changes and it's negative, so that means the original function is concave down. Here we have decreasing, increasing, decreasing. So if we're decreasing and then increasing, we have a min. And if we're increasing, decreasing, we have a max. So we have a min at A, we have a max at B, and we have a change in concavity at C, and we know it goes through this point here. So graphing, we don't really know where that min occurs, but I'm going to put it below. So I'm going to do a min here. I have to pass through this point. At C, I have to change concavity. So maybe I'll do that around here somewhere. And then at B, I have to have a max. Okay, and so I'm saying, let's just do this. And then I've got to change concavity. Something like that could be my first derivative. All right. What are you feeling on 65? Nothing? You're not feeling anything? You looked at that and you said nothing.
Saw the sign.
Yeah, me too. I'm like, I saw the sign. Opened up my eyes. I saw. Okay. What do I know? I have my first derivative. Oops, I'm in green. I'm going to be in black. So first derivative crosses here and here and here. Second derivative here and here. So we can do A, B, C, D, E, just to mess you up. I'll go out of order. All right, so first derivative, A, B, and C. Between A and B, my first derivative is negative. Actually, this is kind of, this one doesn't go on, it starts at A. Between B and C, I am an idiot, that's what I am. Okay.
Between B and C or D?
No, I'm just being stupid with my thing. That's the word of the day, isn't it? All right, so from A to B, I'm negative, and from B to C, I'm positive. This is a mean word. All right, that's my first derivative. My second derivative is, let's see, here's a D, and here's an E. And this will be like a 0, and let's see. Okay, D is negative, positive, and negative. Are y'all following? Okay, so this is concave down, concave up, concave down. This is decreasing and then increasing, right? So we have a min there. All right. So at A we have a min. No, at B we have a min. So original function, we have a min here at B. And then at D and E we have changes in concavity. So it's going to be concave down, then concave up, then concave down. Just like that. Okay? Something like that. So it looks like a shifted sign. All right. 66. For some reason got moved way down here. This also looks like a sign, but shifted. All right, so it's crossing. Our first derivative is the blue one. So that'll be A, B, C. All right, so our first derivative, A and B are in here. It looks like our first derivative is the blue one, so we're negative and then positive and then negative. Decreasing, increasing. So min and then max for our first derivative. Now, from our first derivative. Now our second derivative is 0 just at C. And it's positive and then negative. That's our second derivative. So we have a point of inflection. We're concave up and then we're concave down. So it looks like we have a point of inflection here, we have a min here, we have a max here. And we are told that it goes through this point right here. Okay, and we have to have a min at A, so I'm going to go down, I guess. So I have to have a min at A, and then I have to have a max at B, and then at C I need to change concavity. And I'm concave up at A, and then at C, I'll just change right here. Concave up, and then I sort of change concavity, something like that. Okay? They're almost fun, aren't they? Okay, so now you've done it with pictures. Let's do it with words. 68. I'm actually going to go, what I'm going to need to do is kind of do the work for 68 up here because the way this worked out, my notes aren't very well. So this is number 68. Okay, now these right here, they have given me points on the graph. The point -2.8, the point 0.4, the point 2.0. Now here, the derivative is positive for the absolute value of x is greater than 2. Okay, so we have to remember what that means. For the absolute value of x to be greater than 2, then x can just be greater than 2, or x can be less than -2. Are y'all okay with that? Because like if x were less than -2, like -12, the absolute value of -12 is 12, which is greater than 0. So you may remember from college algebra the greater than symbol with the absolute value, greater. I used to always say you make an or statement. So x, when you have absolute value x greater than 2, you have two possibilities. It could be x's are greater than 2, or it could be x is less than -2. Okay, we also know that here we have our places, what does this information tell you? F prime at 2, F prime at -2 equals 0.
That tells you that 2 and 2 are critical.
Good. Critical points. Y'all with me? And then where F double prime is 0, which they didn't tell us, but if they did, that would be points of inflection, possible points of inflection, although it does appear that they're trying to tell you that the point of inflection is at 0. Okay, F prime of x is less than 0 for absolute value of x less than 2. That's -2 less than x less than 2, right? In between, we have negatives. And we have critical points at 2 and -2. All right, so let's just draw some number line information. Our first derivative number line has the points -2 and 2 on it. And we know that it's positive when it's greater than 2 and less than -2, and it's negative in the middle, which means that the original function is increasing, decreasing, increasing. So increasing, decreasing, decreasing, increasing, right? So we have a max and a min. Now we also know that the second derivative looks like the critical point is at 0, and it's when the second derivative is negative when x is less than 0, so that means it's concave down, and then it's positive when x is greater than 0, so it's concave up. So we have a point of inflection at 0. Why I like these problems is because you didn't have to do any algebra, but you had to show me that you understand calculus. I'm sorry. Okay. So I will come in here and I will draw my graph. I've got -2 and 2. And I know I have and they actually told me -2, 8. 1, 2, 3, 4, 5, 6, 7, 8. So -2, 8 is a point, 0, 4 is a point, and 2, 0 is a point. So -2, 8. Let me pick the thin one. 0, 4, and 2, 0. So I have a max, a change in concavity, and a min. I should have. Okay? Aren't these fun? You wish you were doing it instead of watching me do them. Okay, number 69. Just a lot of notation. See if we can read the notation. So they're saying for when x is less than 2, my derivative is negative and my second derivative is positive. Here's my critical point. When the derivative is 0, those are critical points. So that means at 2, the derivative is 0, so I know that x equals 2 is a critical point. Does that make sense? And 6 is also a critical point. That's what that information means. Now, right, I have a min or max or a cusp. Now, I know that the second derivative is equal to 0 at x equals 4, so this is a possible point of inflection. Okay? All right. So I'll come in here and I'll do a number line for my first derivative where I have critical points at 2 and 6. Now, my first derivative is less than 0 when x is less than 2, so I'm negative. And my first derivative is greater than 0 between 2 and 4 and between 4 and 6. So it's positive between 2 and 6. And then when x is greater than 6, my first derivative is less than 0. Okay, so I'm decreasing, increasing, decreasing. Now my second derivative, its point of inflection is at 4, possible point of inflection. My second derivative is positive to the left of 2, which is to the left of 4, so I can just use that as my test value. And to the left of 4, my second derivative, like 6 is to the right of 4, like 6, I'm negative. So I'm concave down on this interval, I'm concave up on this interval. So I have a point of inflection. I have a change there. Okay, and so I decrease, increase, increase, decrease. So I have a min and a max. All right, here we go. So 1, 2, 3, 4, 5, 6. At 2, I have a min. I don't know where. At 6, I have a max. I don't know where. At 4, I need to change. Oh. Oh, you're right. They did give me the coordinate. They gave me the points. The point 2, 1 is on the graph. 2, 1 is on the graph. The point 4, 4 is on the graph. 1, 2, 3, 4. 1, 2, 3, 4. And the point 6, 7. 6, 7. And I have a max there. Okay, so let me do it in green. Okay, what do I have at 2? I have a min. So I'm going to come in, have a min, change concavity, and then have a min. So, aren't these awesome? Yes, let's do one more because I just can't get enough. All right, good. Sketch the graph of a twice differentiable function y equals fx that passes through a bunch of points and whose first derivative have the following sign patterns. Okay, increasing, decreasing, increasing, decreasing. Okay, so my function passes through a bunch of points. It passes through -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. 2, 2. Okay, it's increasing up to -2, okay? And between -2 and 0, it's decreasing. All right? And then at 0, it starts to increase again, and then at 2, it begins to decrease. Okay, so there is my cool function. All right, and that's actually the whole lesson. Yeah, that's like a record. That was like a 3-hour lesson.